I'm not the author of this paper. And the paper title I present is Unmanned Aerial Vehicle Hub Detection Using Software-Defined Radio. And I'm the substitute presenter of this paper. However, if you have some mathematical derivation problem, you may ask me. And others, please email to the author. And here is the outline. Firstly, we will introduce the research background and the related systems we use in this work. Then we will show the system model and the result of estimate RSSI power. According to this result, we may estimate the communication distance and then propose the trilateration localization method. And lastly, we will show the real-world experiment. Okay, now, about the research background, since more and more private drones be used, the number of incidents involving their misuse is also rising. For example, carry explosive, transporting drugs, and stealing personal privacy and attacking citizens. And moreover, this drone also threat air traffic management. So it is very important to monitor and control the usage of drones. And in this paper, we will focus on estimating the distance of the drones. In this paper, we use WFLY WFT07 transmitter be the UAV remote controller. Here is its frequency range. And most of those controllers use DSS and FHSS encoding mode. In this paper, we focus on FHSS. And the SDR platform we choose is HEC-RF1. It's transmitting and receiving radio signals range from 1 MHz to 6 GHz. In this work, since we focus on distance estimation, the distance measures are the necessary information for trilateration. In practice, these 5 methods are common distance estimation methods. And in our work, we use RSSI distance to measure our distance. Here is our topological configuration of drone controller localization scheme. It is usually necessary to arrange at least 3 transportable monitoring. So we use 3 monitoring stations here, 1, 2, 3. And the measurement we use is shown in this figure. The objective is to calculate the propagation distance from the remote controller to the receiver. So first, we want to find out the power estimation. Okay. To find out the estimated power, we first formulate this equation. And ST represents the transmitted FH signal, HT is impulse response function of the wireless channel, and NT is AWGN. Since the bandwidth and hopping frequencies are assumed to be the priori knowledge, and many narrowband filters are designed to channelize the incoming FH signals. Hence, we may get this kind of output. And according to these 2 equations, we may get RSSI PI of UIT, and it can be estimated as this equation. And according to this equation, we may have average RSSI P, which is we may have the average of this one. We sum all of this equation and average them. And as you can see, in the first equation, all the parameters are known except the beta, and beta is the noise power. So now we are going to estimate noise power. First, segment the output of the filter in short time windows. If the signal to noise ratio is not too low, the signal power can be assumed greater than or equal than to the noise power. Hence, the FH signal is present. Otherwise, this frame contains noise only, so that it will be used to update the current noise power estimate. And we use a simple recursive formula to estimate the noise power, and as shown here. Okay. And according to this equation, we may find out the noise power of each filter, and it can be estimated as this, the first equation. And of course, again, we may use these equations to get the average estimate noise power beta, which can be formulate like this. And according to this beta, we may get RSSIP. However, our goal is to find the estimate distance, which means we find the estimate power, but our derivation hasn't finished yet. So now we need to find the distance. It is easy. We just use the path loss model for signal propagating from a remote controller to a UAV, and which is given by this. And in this equation, P is given, and zeta be the propagation constant, and alpha is the estimate RSSI power we just estimated. So for this equation, it is easy to estimate the distance. We show at that blue block. Okay. After we get the estimate distance, we may have the equation for the each coordinates of the our target. Okay. And now, after we got the coordinates of our target, we may go to the real-world experiment. And this figure shows the real-world experiment. Here, the green circle be our target and also our transmitter. And X1, Y1, X2, Y2, X3, Y3 be the SDR platform, which is our monitoring stations. And now we will use 4 figures to show the results for our real-world experiments. The first figure demonstrates the spectrogram of the record control signal. This spectrogram manifests the frequency hopping patterns of the drone control signal. And the frequency band ranges from 2.412 to 2.422 gigahertz. And the time duration is 100 milliseconds. And the second figure shows the theoretical and measured RSSI over different propagation distance. And where you can see the red node curve specifies the measured RSSI, and the blue curve specifies the theoretical RSSI, and they are really close. And the third figure shows the propagation distance estimation error percentage. And this shows the difference between the estimated distance and the real distance. And the propagation distance estimation error percentage in this work doesn't exceed the 12%. And the maximum percent is at the distance in 20 meters. The last figure shows the estimated position and the actual position of the remote control location. The triangular be the monitor, the three triangle be the 3 monitoring stations. And the red node, the red circle, be the actual control location. And the blue stars be the control location estimates. And here we find out 5 estimated location. And the average of those locations is within 2.47 meters, which is very promising for the future technical deployment to address public safety. Okay, it's a short talk. Thank you for your listening.